password-based key derivation function to calculate a key from a password and then encrypt things with AES. And this is how many systems work. This is how many systems that ask you for a password work, any kind of, like the password on your cell phone and many others. They're turned into a cryptographic key and then used to encrypt things. So you have to install this stuff, which I think I've already done on my Mac here. I think I've already got PyCryptoDome. I can tell by doing this. I know I have Python 3. So if I get out of here and clear, and in fact, let's go up and see if I have a directory for this one, which would be C203. I don't, so let's make a directory and go in there. All right, now I'm going to install this stuff, PyCryptoDome, and you see it's already in there. I've already done it, so I don't even need to use Debian. I can just use my Mac. So I run Python 3. All right, and now I have PyCryptoDome. So the P derivation function works like this. It takes a pseudo-random function, a password, salt, C is the number of iterations, and this is the length of the key you want. So, for example, we can import hashlib. It's in here, and then we can do a help of hashlib. All right, and now it's going to print help pages here, and if I go down here towards the bottom, I will find PBKDF2. These are just the hashes available, pardon me. No, I should see PDF, okay, I should see PBKDF2 somewhere towards the bottom. Yep, there it is, PBKDF2, hash name, password, salt, iterations, key length. All right, so we press Q to get out of there. And now I can derive a 16-byte key with that calculation. Let me see if I can fit both of these on my screen at once. There we go. All right. So this will do it. This will take MD5 as the hash function, and the password is Apple, the salt is nothing, one iteration, and I want a 16 bytes of a key. So that's what it gives me, 16 bytes of a key by doing one hash of this with MD5. All right, so now I can calculate a hash here, just see if you can do it by changing the parameters. Now the key is, the key and the salt here are bytes. It's B, quote. Those are byte strings, not, now this is a string in quotes, and this is a byte sequence, which is a different type of data in Python 3. So to convert among them, there's some useful code here to show you how to convert from one to another. And you'll have to do a bit of that. So now if the password is a 3-digit number, so you have to try all 1,000 of these. There's 1,000 possibilities. And then you know the hash value, so you want to find the password. So what you'll have to do is calculate all 1,000 of these and see which one matches the hash. That's hash cracking. And then this is the most common use case, which I've seen in dozens of Android apps. So let me just run this and show you. All right, so I import AES from CryptoCipher, and now I have clear text, and I've chosen it to be an integral multiple of 16 characters because I don't want to bother with padding. So AES works in blocks of 16 characters. So that's why I put a space at the end. Here's just a sentence from, I think, an ancient Greek tragedy or something. But anyway, this is I think it might be from the Gettysburg Address. Anyway, so now I use PDKF HMAC of MD5, Apple, the same thing before, one round of hashing Apple to make the key. That's the key. So now I make AES with the key, and I'm using electronic codebook, the insecure simple method, where it's going to just encrypt each block separately. I could use a different mode, but this is the simplest mode that doesn't require an initialization vector, just a key. And now I can encrypt it with that. So that's the game. And so this plain text message encrypts into that ciphertext. And from the password, Apple. And this is what happens when you log into your phone or any other system. So you can decrypt it with just the ciphertext and the password. So here is the ciphertext, this 68AA stuff. That's the ciphertext. So you have to make bytes from hex. This is how you take a hex string and turn it into a byte stream. Then you calculate the key from Apple again. I didn't have to remember that key. I just remembered the password, Apple. That will create the key. So I make a new cipher object, and then I decrypt the ciphertext, and there you go. It gets it back. So this is why you can have a human rememberable thing like a password, and inside the system it turns into a long binary key. And this is what they all use. So there's another couple of challenges here where you know the password, you know the salt, you know the hash name and the iterations, and therefore you can encrypt and decrypt things with that information. And this is what's used by virtual machines. Here's the actual key safe used by a VMware virtual machine. This is something that Kirk pointed out to me. Encrypted virtual machines work this way. It has a key safe, and in here, that's what's going on here. This mess here is using PDF KDF2 HMAC with SHA and AES 256 and a salt up here. So all that data is in there. So if you substitute some characters to clean it up, then you can read it. Here's the algorithm for the key. Here's the cipher. Here's the number of rounds. Here's the salt in base 64. And here's the encrypted data in base 64. So you can do it all. You can import base 64 to decode the base 64 pieces. That will give you the salt. This will give you the data stored in the vault. You can deduce the key here. And in this case, I tell you what it is. It's 123123 was the password to get in here. And so that will turn into the key, and you can decrypt it, and you get the result, which is, this is what was in there. Type equals key, AS1. What was in there was, in fact, an AES key. That's what you typically do. You have a vault, which is encrypted with a password, and what's inside there is an AES key, and you encrypt all the rest of the data with AES. This is how HTTPS works, and it's also how hard disk encryption works. You don't want to bother doing public key decryption of all the contents of a disk. That would take too long. You use AES for that, and the only thing you use public key encryption on is this here. Oh, this is not the only thing. Anyway, the only thing you put in the vault is the key, and that's just controlled by a password. This way, you could change the password, and it would just change this encryption. It wouldn't have to re-encrypt the disk. So that's the game. And here's another one. Here's where we have only some information about the key, but there's 1,000 possibilities. And here's one where you have a harder safe, where you only know the first two characters are we, and the last two characters are SS. And there's 8 characters. There's 4 letters in the middle you have to guess, and you have to crack in. So that's how this system is actually used in practice. That's how any system works that asks you for a password, typically, and then encrypts something. So that's another project to try.